due to so we would like to have an in-depth understanding of the subject through this course. Now, clearly, the subject has two parts. One, the first part is statics, and that eventually leads to solving equilibrium problems. But there are few other topics that we must consider before arriving at equilibrium, and actually some of those topics are much more important compared to equilibrium. And the next topic in hand is dynamics. Okay, so even the dynamics has two parts, and you must already be familiar with the terms. So there is kinetics and kinematics. Okay. Now, more or less, the static part would be, the syllabus for you for your first class test, and mostly some portion of the statics, and mostly the dynamics part is going to be in the second class test, and the entire syllabus, as usual, would be considered for your semester exam. Okay. In statics, the topics that we want to consider serially are like, the first one is like vectors. We would be considering different aspects of vectors, and the second chapter would be, or the second topic that you would like to discuss is, which in my opinion is most important, and that topic would be equivalent force system. Okay. And then comes few topics. Firstly, there is equilibrium, general portion of it, so the general version of equilibrium. Next, we would consider equilibrium with friction. Okay. And there is a separate topic which is properties of surface. Now, that is not directly related to any of the topics, either in statics or dynamics. Okay, but that subject is important if we for more advanced topics in engineering mechanics. Okay, so and also a little bit of application of properties of surface is there in equilibrium. Okay, but mostly this topic is important for an advanced subject called solid mechanics of or strength of materials. Now, when we are looking into having an equivalent force system and eventually solving an equilibrium problem, there are two types of objects that we want to consider. Actually, the objects are not different. The object is everyday real life objects. Okay, but it is how you want to model them. And as you study more and more engineering subjects, you realize that that's what we do in engineering as well as in physics, that we try to model real life objects, real life situations in some mathematical equation. So the most crude mathematical model that you will be encountering in mechanics is called a particle. And although I'm drawing it as like with a finite space, okay, the particle is supposed to have zero dimension in any direction. Okay, uh, it I mean, the particle that we are talking about in relation to classical mechanics here, it does have mass, okay, but it doesn't have any dimension. Okay, now again, there is no real life object. Okay, I mean, if you look into from the point of view of classical mechanics, there is no real life object with zero dimension and finite mass. Uh, but then, if you try to model certain object like that, it helps you pose a problem and also to solve the behavior of the, or to predict the behavior of the object pretty accurately uh, without much of complication. And of course, such models have their own set of application. For example, if you were uh, trying to do the analysis of, let's say, dynamics or statics, okay, of mm, of planetary motion. Okay, so there is your sun, and let's say there is another planet that is performing a motion. Now the planet itself is much smaller compared to the path that it is taking. So at any point on the path, if rho is the radius of curvature and the characteristic dimension of the planet is L, so L is much smaller compared to rho. And in a situation like that, when the object itself is quite tiny compared to its surrounding, you can model that as a particle and may get pretty satisfactory result. So that is one of the models. In this whole course, we'll be encountering particles, that is objects that we model as dimensionless, and then there is another model called rigid bodies. What are rigid bodies? Now, if the object is larger, so much so that you cannot really neglect its dimension, and you cannot really neglect its rotation on top of its translations. So if you were modeling it as a particle, what would matter in 3 dimensions is its translation in 3 directions, x, y, and z. Okay, but if it is not sufficient to describe the motion of an object only through translation, if you need to mention the rotations, and also the dimension of the object is much larger, so that you cannot simply neglect dimension. Okay, so you can go with the rigid body model, but as the name suggests, that the dimensions may be finite, but the changes in the dimension, let's say L is the characteristic dimension, so delta L by L, the changes in such dimensions must be much smaller compared to the dimension itself. Okay, or in other words, you can start with 2 points on the object A and B, and let's say that distance is LAB. Okay, so so under the given set of given circumstances, okay, if the changes in that dimension is much small, okay, it's quite negligible, then you can treat that object to be a rigid body. Okay, now the whole point of discussing about particles and rigid bodies is twofold. The first part is to accept the fact that we are not really solving what really happening. Okay, because to be frank, real life objects are also not rigid, they are deformable, and they undergo strains, and as you may know, this quantity itself is defined as strains, defined as a strain. Okay, this is a strain measure. Now we don't discuss about strains, okay, until we arrive at this subject, strength of materials. Okay, in the domains of engineering mechanics, this first course, okay, here we would be happy with only these two models, the rigid bodies and the particles. Okay. In strength of materials, there is another advanced level model. Okay. And that model is continuum. And it's couple of U's and then M. And that model is also not kind of a fundamental model, or that is also not the absolute model. There we do accept that the object deforms. Okay, and this time I'm just going little ahead of time because we are not will not be discussing continuum models. So here we do accept that the object may deform. Okay, but here we try to model the object as if I were to draw a line, an imaginary line, with the coordinate along that imaginary line being S across the body, any property of the material need not be constant, let's say density, need not be constant, but would be changing continuously. Okay, there is no gap. But if you really think about it, an object would be made of atoms and molecules. Okay, and that is, you know, in the angstrom level. Okay, that is 10 to the power minus 10 meters. But you don't have to go to that meter. Even if you are in the micron level, okay, 10 to the power minus 6 meters, then also there are certain things called grains, which are basically a stack of atoms. Okay, and usually the real life objects, day-to-day objects, are multi-grain materials, and those grains, okay, are oriented in different directions, and those grains have grain boundaries. So if I exert this diagram over here, so there is one grain like this, then there is another grain like this. Okay, so there is something called a grain boundary, which is the region of discontinuity. And if you really plot this diagram over here, it's actually not going to be. So if I really draw my S coordinate with you know, among the set of grains over here, it's not going to be a continuous line. It may be varying across a grain, it may be continuously varying. Then at the grain boundary, it's just non-existent. Then it starts on the other grain, and then it is non-existent. Okay, so basically it's a discontinuous curve. Okay, in reality. However, in the domains of strength of material, we consider them to be a continuum, which means the property is changing continuously. There is no gap. Okay, so all I'm trying to say here is we are actually, you know, the very basic level of modeling. Even an advanced course would be dwelling in the domains of model. Okay, a very crude model at that. Even the continuum model can be regarded as a crude model, which works in the macroscopic scale. It works because, as I mentioned, the grains are of the order of microns. Okay, but if your object has the dimensions of several hundred millimeters, so obviously you can, you know, work with the continuum model. And to be frank, even the strains that we are talking about, for most materials, these strains are within the limits of 10 to the power minus 3. The objects that we use, okay, for let's say constructing buildings or for lifting a heavy weight, okay, those objects, in those objects, okay, as long as at least they are within the elastic limit, the strains are smaller than 10 to the power minus 3. That is 1 in 1000 is the, you know, the limit of the change that is happening of the dimension. Okay, so just like the continuum model finds its place or applicability, as I mentioned, same way the rigid body model also finds its application. It's just that in some situations we cannot really work with the rigid body model. Okay, but then here we would be exploring these two models, the particles and the rigid bodies, Okay, and you'd see how far are they applicable. And number one, and number two is that although for statics we would be studying the equilibrium of both particles and rigid bodies, the dynamics part in your syllabus is restricted to both kinetics and kinematics only for particles. Okay. Okay. So that is regarding the more or less the outline of the course. We can discuss few other things, but before going into that, um, let me know if you have any question. No question? Okay. Okay. So what I'll be doing is,
স্যার ক্লাস
let's discuss.
টেস্টের কবে হবে সেটা নিয়ে ডাউট ছিল।
হ্যাঁ হ্যাঁ, ক্লাস টেস্ট কবে হবে?
হ্যাঁ হ্যাঁ,
ক্লাস টেস্ট সিলেবাসটা যেদিন কভার হয়ে যাবে তারপর দিন হয়ে যাবে। ওকে, আচ্ছা। So let's discuss the books, textbook. So yeah, the title of the book remains the same as the name of the subject. Okay, and author Miriam and Craig. Okay, so this book has two volumes, separate volumes for statics and the dynamics part. Okay, in addition to these two volumes, I would suggest that the title still remains the same, Engineering Mechanics. Okay, the book by R.C. Hibbeler. Okay, so this is a single volume book consisting of both the statics and the dynamics part. That this book is highly recommended. For the reason is the order in which they have discussed mostly the statics part. The second book has been really patient with the build up of the understanding. Okay, whereas I find the first book, your textbook rather, is slightly going back and forth with the order, and at times a bit confusing. I'll be following either of the books, and the problems that I will be doing in the class would be from either book. So that is there, but the second book is highly recommended. The first book is kind of the standard that we follow for across all the departments, but I would suggest you can follow at least for the initial part. If you follow R.C. Hibbeler, that would be good.
Can you share the PDF of the second book?
I actually do not have the PDFs. Okay. 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 What else? Okay. So you are already familiar with the primary units, right? So unit of mass is kg, unit of time, second, and distance, meter. All of this you are familiar, and mostly you would be doing problems with metric system, but at times we might also encounter problems in British system. Okay. Now, now you know the unit of force, right? We need to know the unit of force. What is the unit of force in metric system?
Newton.
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 Okay. And if it is Newton, how do you represent that with kg, meter, and second?
kg meter per second square.
Kg meter per second square. Good. Now try this with British system. Have you heard of 1 kg force?
Yes, sir.
Yes, sir.
And how much is
Yes,
that in
sir.
Newton?
In
How much is
1
that in
Newton.
Newton?
in
Huh?
9.8 Newton.
9.8 Newton. So whatever the value of G, that needs to be multiplied, right? So if G is, G at certain location, right? So G is about 9.81 standard value meter per second square. So it is that much Newton, which is approximately 10 Newton. Okay. Now,
Yes, sir.
have you ever felt how much is 1 kg weight? Have you ever picked up 1
Yes.
kg weight? Okay. So you know how much that weighs, right? Now, have you ever thought that 1 Newton is about 100 grams in weight? Have you thought in this way? That's what it translates into, right? That 1 Newton is around 0.1 kg force, and 0.1 kg is 100 grams. Have you ever thought in this way? So you now have the understanding of how small a Newton of force is. Okay. And now imagine the unit of pressure. Although in your course there is nowhere you would be using, I guess nowhere you would be using this unit, Pascal. Now you have probably left probably lifted 5 or 10 kgs in your hand. Okay, and imagine how small that area is, the area of your palm. Okay, and now imagine lifting 100 grams of weight, but with an area of 1 meter squared. 1 meter squared is so much big area that 4 people can stand in that area. Okay, now they won't be allowed to stand because of social distancing and all, but it's that much large area. So so at times, so the point of this discussion is that it's not good enough to know what is the conversion of certain unit to certain other units. Okay, you need to have an understanding of how much you need to have a feel of how much any quantity is. Okay, So possibly a lot of times you would be encountering problems with several kilonewtons. Okay, because Newton is such a small load, a lot of times you'll be encountering problems with kilonewton. Okay, so so that is there. Okay, now can you tell me what is the unit of mass in British system?
Pound.
Pound.
Pounds.
Okay, so we write it like LB, or at times we also like write it as LBM, right? Okay, unit of time is second, no issue, and distance can depend. Okay, you could be taking inches or yards or feet. Okay, okay, so so what is the unit of force in British system?
Poundal.
Sir, again.
Sorry,
Sorry,
what is
sir,
the unit
please
of
again.
Pound feet per second square.
it's yes, obviously it will be pound feet per second square, but do you know what it is called?
Poundal.
Poundal. Okay, but in British system hardly that unit is used. What is the unit do you think is used in British system? It is actually pound force. Okay. Now, can you tell me what is the relationship between Kgf and Lbf? Which one would be greater?
Sir, pound force.
Sorry,
Pound force. LBF.
pound force would be larger. See, there is only one thing that we still purchase in pound.
Sir, KGF is larger, sir.
Kgf is
KGF.
It's roughly 2.2 pound force.
roughly 2.2. So, 2.2 lbf. Okay. Yes, correct.
It is 4.4 newtons lbf.
lbf is 4.4 Newton. Okay, that is also correct. Okay. But can you tell me how that works? How so?
Sir, can you repeat your question, sir? Didn't understand.
Yeah, the question is, how does that relation work out? Where does that come from? I mean, you know that Kgf and Lbf has such a relation, but where does that relation originate? Actually, it's not a question. All I'm trying to say here is actually you see, these are gravitational units. Okay, it's the unit mass being pulled by the gravitational force. So the acceleration part is the same. Okay, it can be written as 9.81 meter per second square or about 32 feet per second square. Okay, I mean, just now you mentioned another unit, poundal. So that unit, okay, is 1/32.2 of lbf, right? But I'm not asking for the relation between poundal and Newton. All I'm asking is the relation between pound force and kg force, and these are the forces with which gravity pulls certain unit mass. So the gravitational pull part, the acceleration part, is this quantity, this much meter per second square or this much feet per second square. So the relationship between Kgf and Lbf is same as these two units of mass. And yes, 1 pound mass is, around 450 grams or 0.45 kg. So that works out that Kgf is approximately 2.2 lbf. Okay. Now, unlike metric system, in British system, exclusively lbf is used. In metric system, a lot of times kg force would be used. Not a lot of time. A few times kgf would be used. Newton or kilonewton finds way more applicability. Okay. Whereas in British system, lbf is exclusively used. Okay. And that can be at times a little bit of challenging. Okay. Let's say if there is an external force, okay, acting on a disk, which is given in, let's say, 50 lbf, and the weight of the object is given to be 100 lb. Okay. And for some reason, so I mean, not 100 lb or 100 lb. Okay. Let's say I'm interested in finding out the acceleration. Okay. So then it might be necessary for you to remember the conversion unit from gravitational to standard unit. Okay.
স্যার পরীক্ষায়
So
সিস্টেমে কোশ্চেন আসতে পারে?
পরীক্ষায় ক্লাস টেস্টে আসতেই পারে। ওকে, সেমিস্টারে আসতে পারে কিনা বলতে পারছি না, ঠিক আছে। সেমিস্টারে কমন কোশ্চেন হবে কিনা সেটাও বলতে পারছি না এই মুহূর্তে, ঠিক আছে। বাট there is no reason for আমি যতদূর জানি that the APS system is acceptable. Okay, so there is no reason for you to think that APS system would not be included. আমি জানি না কেন এরপরে যে টপিকটা বলবো that is included in the first chapter. That's a bit confusing for me. Okay, actually the chapters I just discussed, there was vectors, and there was equivalent system, and equilibrium. Okay, so actually these two in your textbook is the second chapter, I believe, and this one becomes the third chapter. Acha, I forgot to mention one thing in equilibrium. In addition to so there is general equilibrium problems of particles and rigid bodies, then there are with friction, and then there is another chapter called structures. So when you include more than one rigid body, okay, so there are trusses, but trusses are not included in your syllabus. You would be working with frames which include more than one rigid body as an assembly. Okay, and when you study the equilibrium of that would be a part of structures. The very first chapter of the textbook is actually again an introductory chapter that does all of this that we just did. In addition to that, it also introduces vectors, types of vectors. Okay. But before going into the details of types of vectors, we need to know what are the things that we need to know to describe a quantity. Okay. Now, I have been saying vectors a lot. Now, there are certain quantities which are scalars and certain quantities that are vectors. Okay. And as you study more and more, you would realize there are other quantities that are matrices, okay, and higher orders of tensors. So the general, I shouldn't be bringing tensors in the first class of engineering mechanics, but a scalar is a zeroth order tensor. That means I can simply write it to be A. A vector is called a first order tensor. Okay. And as you may be already familiar, I can represent it, let's say, in Cartesian components as ax, ay, az. Okay. Then there are certain quantities. So this one is called a first order tensor, which means I need to use one index to represent each of the components. Okay. I don't know whether you are familiar with moments of inertia. Okay. So that is the second order tensor, and I can write them to be ixx, iyy, and so on. Okay. And then there are higher order tensors. Okay.
Sir, is it
Now,
possible to explain what is a tensor in?
What is the tensor? Tensor is, you see, tensor is an organized way of representing quantities. Okay. You already are familiar with vectors, right? In the Cartesian components of vectors, right? Although we would be discussing thoroughly about Cartesian vectors, and while we will be doing that, we'll be assuming we know nothing about Cartesian representation. Okay. So you can understand that there are quantities, okay, maybe with the certain likelihood, okay, like the speed and the velocity. It is sufficient for speed to just, you can write it with a single value, right? Whereas to represent the velocity, okay, you need more than one component to represent that in Cartesian form. Okay. Now, there may be quantities, for example, moments of inertia, they are kind of written like this: ixx, iyy, izz, ixy, ixz, iyz, iyx, izx, zy. Okay. Now this systematic arrangement is important because we know what moment of inertia relates to. It relates between the applied, so consider this to be mass moment of inertia. So you have applied certain torque, and later on, as we progress in our course, we realize that the moment or the torque is also a vector. Okay. And the angular acceleration is also a vector. Now, if there are two vectors on two sides and there has to be a linear relationship, okay, what comes in between? There is a matrix. Okay. And in this case, that is the moment of inertia matrix. And that is the second order tensor. That means to represent each component, you need two indices, two independent indices, x and y, x and z, y and z, etc. Okay. Now again, this is beyond the scope of our subject, but to give you a glimpse of, this progressing order of tensorhood, where to represent a scalar, you don't need an index. That's why it is regarded as a zeroth order tensor. To represent a vector, each component of a vector, you need one index. Okay. Then there could be higher versions of that. Okay. And there could be even a third or a fourth order tensor. Okay. এখান থেকে কি কিছু আইডিয়া করা গেল কি বলতে চাইছি? গেল না?
স্যার এটা কি মানে মোটামুটি ওই সিমিলার টু একটা ফাংশন, মাল্টিভেরিয়েবল ফাংশনের হেসিয়ান আমরা যেভাবে লিখি সেটার মতো, সেটাকে কি আমরা টেন্সর হিসেবে বলতে পারবো?
সেটা অবশ্যই একটা টেন্সর, বাট a Hessian is like a double derivative, right? I mean, Hessian is as much a second order tensor as a gradient is a first order tensor. ঠিক আছে? I mean, that is just a special case. Okay. Anyways, you being electronic engineers, you would be encountering tensors a lot. Okay. So there is no point bothering about that right now. This just consider that to be a glimpse. Okay. So the gross statement that I'm trying to make here is that to represent a scalar, you don't have to mention component, because that is the components are not there. Vectors have components. Okay. Or in other words, you already know the word that the scalars can be represented with a magnitude, and the vectors need magnitude as well as direction. For example, that earlier example that I gave you, that there was speed and a velocity. For a particle moving with certain velocity, you can determine the speed as well, right? The speed is essentially the magnitude of the velocity. You add the direction to that speed, that becomes the velocity. এই পয়েন্টটাতে এগ্রি তো করা যায়। So, okay, but my point here is that is it sufficient to only provide the magnitude, or to only provide the magnitude and the direction? We know that the scalars have magnitude, they do not have directions. Vectors have both magnitude and direction, but are they sufficient to describe a quantity? That is my point here. Let's focus on this topic, this sentence. So do you agree that they are sufficient to describe a given quantity? Is it sufficient to describe a... Sorry?
আরেকবার রিপিট করবেন?
So we know that scalars have magnitude but no direction. Vectors have both. But my point is it sufficient to describe a scalar? I mean, is it sufficient to is magnitude sufficient to describe a scalar, or is it if magnitude and direction together is sufficient for describing a vector, or do you need other things to describe those quantities? আচ্ছা, একটা ব্যাপার তো বোঝা যাচ্ছে that even for scalars magnitude is not sufficient. I mean, if I ask you how old you are, and let's say you say 18, okay, it is inherent that you mean years. Okay, so only magnitude is not sufficient, you also need the unit. এটা তো বোঝা যাচ্ছে যে ইউনিট লাগে।
Sir, in case of vectors, mathematically speaking, when we define vectors, we should also define a point of reference.
Point of
reference?
What do you mean by point?
তখনই তো পয়েন্ট অফ রেফারেন্সটা মিন মানে বাই ডিফল্ট বলে দিচ্ছিস।
Point of reference, I'm not happy with the answer. Okay, if it had been point of something else, I would be really happy. Anyways, I mean, for me, the point of reference doesn't make a lot of sense. Okay, so I would go there, but before that, let's establish that you need, even for scalar, we need certain other things. For example, unit is important. But then certain scalars could as well be unitless, like the specific what is it called, specific density, typically represented in fraction. Is it called specific density or specific gravity? What is this called?
Specific gravity, it's interchangeably used.
Okay, so whatever, so there could be scalars with units, there could be other scalars which do not have unit. Same applies to vectors. Okay, for example, unit of velocity, okay, could be meter per second, okay, or kilometer per hour. Okay, so obviously it would have components in x and y or any other direction. Okay, so in addition to having magnitude and direction, it can also have unit. Can you think of a situation where a vector doesn't have a unit? I can think of one. So if I am given a velocity, I can represent that with the magnitude of the velocity, which is essentially the speed, and speed does have a unit. Multiplied to that is the direction of the velocity, or the so-called unit vector. Although it goes by the name unit vector, it is actually unitless.
So can you repeat this last part once?
Yes, my question was, can there be a vector without a unit, just like a scalar? And what I'm trying to say here is, a unit vector can be regarded as a vector which is unitless. Okay, I mean, you can use the same unit vector to define some other quantity. Okay, for example, let's say a particle is trying to move from point A to B, and the simplest way we can define a vector between A and B is called a so-called position vector. And if the vector is from A to B, we represent that as position vector of B with respect to A. Actually, we use R for that. So it is called a position vector of B with respect to A. Okay. And a unit vector along AB, and that this one has a unit of, let's say, meter. So the position vector of along AB is essentially, sorry, the unit vector along AB is the position vector divided by its magnitude. Now, if I were to, represent the velocity of the particle, that would be the speed, which is the magnitude of the velocity, times this unit vector. Okay. So the unit of the quantity, which is, let's say, meter per second, that is embedded in the speed part. The unit vector doesn't carry a unit. Okay. Does this sound okay?
Sir, but the unit vector carries a directional notion.
Okay. Are you familiar with the unit vector? The term unit vector?
Yes.
Yes, sir.
Okay. So how do you perceive that? How do you understand unit vector?
A vector of unit length in a particular direction.
It's vector of unit length in a given direction. Yes, but don't be confused with the term length. Okay, because in that case, in your mind, you have a unit for that, and that is meter. Okay. Yes, it has a unit magnitude. but it not necessarily is a length. Okay, is just an abstract, a mathematical representation. It's not a real quantity. It only helps you, understanding the direction of a given quantity. It doesn't come with a unit. And the definition that you used, in that the very term length, yes, it is the magnitude which is unity, but the term length is misleading. It's not talking about any length.
Length in a vector space, as in not in like medium
Yeah,
space.
it's an abstract quantity. Basically it's a magnitude. Okay, so it's a vector of unit magnitude in a given direction. That way it would be. As you can see, the transferability of the unit vector from quantity to quantity requires it to be dimensionless. Okay. I mean, since you are familiar with Cartesian components, if I give you I, j, and k, the unit vectors along x, y, the global x, y, and z axis, can you tell me what are the units of I, j, and k? There are none. The unit vectors, by definition, are supposed to be dimensionless. Okay. So this much may not be, that. This much may be something that you can arrive at very easily. But with vectors, there are few other things. Apart from these quantities, such as the magnitude, direction, then your unit, there are few attributes of a vector. One is called the line of action, and the other one is called point of application. Okay. And what I'm about to discuss is, I don't know why, has been discussed in the first chapter of your textbook. Okay. Because the explanation for this comes in at the end of the second chapter, nearly at the end of the second chapter. Okay. But I'll try to explain that. So there are three types of vectors. One is called a fixed vector. The second is called a sliding vector. The third one is called a free vector. Okay. Now, what is a fixed vector? A fixed vector has a fixed line of action and a fixed point of application. Please try to understand what I'm saying here. This line and this line, okay, or you see this vector u and this vector u prime over here has the same magnitude and the same direction, but the two of them are not the same vectors. Their lines of action are parallel to one another, but not the same line. They're acting along different lines. Okay. Now, here we have another vector, same magnitude, same direction, u double prime. So it is collinear with u prime, but it is not acting at the same point. The point of application is different. Okay. So to completely specify a given vector, okay, you might require all of these attributes. So there are 5 of them. And this is the maximum that you require. Okay. And here we are talking about special cases where you might require less. So a fixed vector, as the name suggests, for which you need to specify all the 5 attributes. You see, these 3 are mandatory. Magnitude, direction, and unit are mandatory. You might need the later 2, one of the later 2, or none of them. So fixed vector is one for which you need all of these to specify the vector. Okay. To understand what that would be, you cannot be within the domains of rigid bodies. This one is a deformable body. Okay. Now here I'm applying a force of given magnitude, direction. Okay. Now the effect of the force is, of course, it can, provide, if it is supported somewhere, it can provide equilibrium. If it is not supported, it can, generate certain amount of acceleration, or because it is not passing through the center of mass, maybe it can generate another moment, okay, and cause the rotation of the object itself. Okay, so it could be rotating about the center of mass, center of gravity. All of these are there. Okay, and all of those would be there even on a rigid body. Okay, so what are the things can happen? It can produce a moment about, center of gravity. Okay, now, okay, what I'll do first is I'll just consider this one to be a rigid body, because its line of action is not passing through center of gravity. It would be providing a moment. Okay, that means it can cause, and imagine it is not also supported over here. So not only does it cause an acceleration, it would also be causing a moment about CG. So there would be an angular acceleration. So both linear and angular acceleration. And that would happen on the rigid body. Okay, and that would happen on the rigid body in the same way. Instead of the force being applied on the line of action on the left side, instead of it were applied at the right side or the bottom side. Okay, so you can transfer a force along its line of action anywhere along its line of action, and you can get the same result for a rigid body. So force on a rigid body is a sliding vector. So you can slide a vector along its line of action. So the line of action is fixed, but if you change the line of action, there would be a different moment and the effect would be completely different. Okay, you cannot change the magnitude and direction of the force, otherwise the acceleration would be different. Okay, unit, of course, you cannot change. You cannot also even change the line of action, because otherwise the moment would be different and the angular acceleration would be different. But if you want to keep all the effects same on a rigid body, you can at least change the point of application. So this one you can change for a force on a rigid body, and therefore a force on a rigid body becomes a sliding vector. এই পার্টটা কি বোঝা গেল?
Sir, can you please repeat once more?
স্যার
I'll repeat once more, but I need to know where you are stuck.
স্যার একটা জিনিস, এই মানে অল স্লাইডিং ভেক্টর জন্যই কি এটা বলতে পারি যে পয়েন্ট অফ অ্যাপ্লিকেশনটাই চেঞ্জ হতে পারে?
That is the definition of a sliding vector, that it can be it can slide along its line of action, and it doesn't have a fixed point of application.
Okay.
And it can be shown for a force on a rigid body that its point of application, exact point of application, doesn't matter.
Okay, sir. ঠিক আছে.
As long as it is acting on that body, anywhere on that body, on that line of action, it is going to produce the same effect. You see, the moment is going to be same. The normal distance to the force from the center of gravity That doesn't change if you slide the force along its line of action. Okay, so moment is same, the force is same, so it is going to have the same acceleration and same rotation. And those are the only type of motion that the rigid body can have, because the rigid body cannot deform. It can either translate or rotate. So what would matter? The linear acceleration and the angular acceleration. And what would they depend on? The inertia, both linear and angular, and also the applied force and the applied moment. Okay, so therefore for a rigid body, it doesn't matter at which point on its line of action the force is actually acting, and that's why the force on a rigid body becomes a sliding vector. এই পার্টটা বোঝা গেল?
Yes, sir.
বোঝা গেছে তো? আচ্ছা, যদি ডিফর্মেবল বডি হতো কি হতো? যদি এই বডিটাই ডিফর্মেবল বডি হতো, তাহলে it's not just the line of action that matters, its exact point of application would matter as well. Try to understand. If I apply a force at the top surface, it would probably compress because of the applied force. It would deform and it would compress because of that force. So in addition to having certain translation and rotational motion, it is also going to have certain amount of deformation because of the force. And that would change depending on whether am I applying the force on the top surface or at the bottom surface. So instead, if I choose to apply the force at the bottom surface, I'd be developing a different type of deformation, this time because of tensile force. Okay, so effect is not the same, and therefore the force on a deformable body becomes a fixed vector. এটাতে এগ্রি করা যায়?
Yes, sir.
এটা বোঝা গেল তো? আচ্ছা, the third one is a little complicated. So imagine you have a rigid body and you have a couple. That means couple of forces which are same in magnitude, opposite in direction, but non-collinear, which means but acting on the same body, which means they do not give you an equilibrium. The net effect of the two forces is a couple moment, okay, a tendency of rotation. Later we will see that the couple is also a vector represented by cross product and all. So that couple, okay, depends only on two quantities: the magnitude of the forces and the normal distance. I mean, the same couple could be generated. Here we are actually doing a little bit of equivalent force system as well, which is in our syllabus, the second chapter. I mean, the same couple could be created by the same two forces, but this time oriented in a very different direction, maintaining the same distance. Or the forces could be multiplied by 2 and the distance could be divided by 2 and the direction of the forces could be changed. And even it can be shown that the same moment can be created by applying, and this thing we will see in a later stage of our course, that even if those set of forces acting at a different location, okay, maintaining the same distance, okay, would be able to produce the same moment and would be causing the same I mean, the fun fact with the couple moment is this, that this moment, okay, is essentially the moment due to the positive F force and the moment due to the negative F force. Now the question remains about which point. The answer is any point. That means you could be taking the moment about this point or the center of gravity or anywhere outside in the space of these two forces individually and add them up, and the net effect is going to be this couple moment. So it doesn't really matter where exactly the force is acting. Okay, so in that case the couple is a free vector, or the moment due to a couple. But only on a rigid body. How is that going to be so? That we will see in a later stage. But the moment turns out to be identical whichever point you take as a reference. Okay, about which about every point within the body and even anywhere within the space, it is going to be the same. The crucial thing is that while you are taking these forces F and F, you can change the direction. Okay, you can change the magnitude and the distance, inversely proportional. Only thing is you cannot change the plane of the forces because the moment has to be perpendicular to that plane. So the moment itself is a vector. How is that a vector? We'll see that in a later stage, and that has to be perpendicular to the plane. Okay, so only thing that you cannot change is the plane of the two forces. Okay, so you can create the same effect on the rigid body. Of course, if you are a deformable body, there would be different set of deformations based on which couple do you take, which diagram do you take, but in every situation, a rigid body would have the same response. If it is free to rotate, it would rotate with the same angular acceleration. If it had been supported somewhere, if it had been fixed somewhere, okay, to be in equilibrium at the support, it would develop the same amount of your reaction moment. Okay, so the net effect on the rigid body would be same because of a couple moment, irrespective of where you are actually applying the couple moment. So now try to understand the direction, of course, of the couple moment is crucial, so it cannot change. The fact that the magnitude is not changing, you are ensuring that with that inversely proportional law, unit of course is going to be the same. What you are allowing to be same change is of course the exact point of application. And also, since it is perpendicular to the plane, by shifting the forces, you are let's say this one is the perpendicular over here, and this one becomes the direction of the moment over here. But when you shift the forces over here, it's the same parallel line, but the direction remains parallel, but it's not the same line. So the line of action keeps on changing. So the line of action of the couple moment also doesn't matter. Okay, and that's why it becomes a free vector. It can shift anywhere. You could be applying that couple anywhere to the rigid body, and you are still going to get the same effect. এই অবধি বোঝা গেল?
স্যার ডিফারেন্ট জায়গায় করলে মোমেন্টটা আমরা ইচ ইন্ডিভিজুয়াল পার্টিকেল অফ দ্য রিজিড বডির উপর তো ডিফারেন্ট এফেক্ট আসবে, যদিও টোটাল এফেক্টটা সামড ওভার দ্য রিজিড বডি সেম হবে।
এবার মজাটা কি, আমরা যেহেতু ধরে নিয়েছি রিজিড বডি, ইন্ডিভিজুয়াল পার্টিকেলের উপর কি এফেক্ট হতে পারে? ইন্ডিভিজুয়াল দুটো পার্টিকেল একটা আরেকটা থেকে দূরে সরে যেতে পারে বা কাছে চলে আসতে পারে, বাট দ্যাট হ্যাজ বিন প্রোহিবিটেড বাই অ্যাজিউমিং ইট ইজ টু বি আ রিজিড বডি। So there is no effect, okay, on a rigid body. There is no localized effect. The only sort of motion that the rigid body can have is 3 translations and 3 rotations in 3D on a plane, 2 translations and 1 rotation about z-axis. Okay. Had it been a deformable body, any 2 points on the deformable body could have a relative motion, relative change in the distance, or the change in the the distance between the two, okay, under certain externally applied force, okay, and that change in distance between any 2 points on a deformable body normalized with the original distance is called the strain. But there is no question of strain, so you can again, you said particles of a rigid body, but you need to understand we are not even considering deformable bodies here. But in the course where we actually consider deformable body, that is strength of materials, there also we consider the object to be a continuum. There is no particle, it's just a a single blob of material, need not be homogeneous. That means the properties such as density need not be changing, need not be constant everywhere, but it is changing continuously. It's not a discontinuous curve. Your idea of particles, your idea of a rigid body composed of particles, okay, that is even one step advanced model, which we are supposed to consider in strength of materials. Even it is advanced compared to the continuum model. So you can think of even the rigid body to be a continuum. It's just that not particle, but 2 points in that continuum cannot have a change in distance between the two. When we talk about a point, that is a location in a object with finite dimension. A particle is an standalone object with 0 dimension.
ইয়েস স্যার, ওটা বুঝলাম, বাট আমি বলছি যে ডিফারেন্ট পয়েন্ট ইন আমরা যদি একটা একটা পার্টিকুলার লোকেশনে একটা মোমেন্ট অ্যাপ্লাই করলাম, আর অন্য একটা লোকেশনে সেম মোমেন্টে অ্যাপ্লাই করলাম, আর আমি বলছি যে দুটো কেসের জন্য ডিফারেন্ট পয়েন্ট, মানে একটা সেম পয়েন্ট অফ আ বডি দুটো কেসের জন্য তো ডিফারেন্ট বিহেভিয়ার, মানে যদি একটা ইম্পালস দিই, মানে মোমেন্টটাকে একটা ইম্পালস হিসেবে দিই, তাহলে ভেলোসিটি তো ডিফারেন্ট হবে, বিকজ ডিসটেন্স ফ্রম দ্যাট পয়েন্ট অফ দ্যাট ইম্পালস ইজ ডিফারেন্ট।
এবার বলি কি বলছো। The moment, one second, can I answer his question first?
Okay, sir.
Okay. So the exact location of application of a given moment, or rather actually application of a given force, or rather the line of action of a given force would matter, okay, if that is a single force. But as soon as you have 2 forces of equal magnitude, opposite in direction, okay, but non-collinear, that becomes a couple, and sum of the moments due to these individual forces, which essentially is the couple moment, okay, that moment is independent of its source. That means, look at this diagram, whether that moment has been created by figure 1 or figure 2 or figure 3, okay, I mean you can change the direction of the forces, magnitude of the forces, okay, but not changing the plane first of all, and obeying the F times D value, it is going to have the same effect on the rigid body, okay, because the effect on the rigid body depends on effect on the rigid body depends on whatever is the moment due to all the forces. First of all, the acceleration. Newton's laws, right? Sum of forces is mass times acceleration. That applies to rigid body as well. Although Newton's law was originally proposed by Newton for particles, but that applies to rigid bodies as well, with a tiny change. And can you tell me what change would happen when you are using Newton's laws for rigid body? The change is, first of all, you have to understand
there is a point of application is important now.
No, not that. Summation of forces is still mass times acceleration, but mass times acceleration of the center of mass. You see, the object itself, other than translating, let's say the center of mass is translating, okay, and other than the translation of the center of mass, the entire object could be performing a rotation about the center of mass, which means the different points on the rigid body, okay, could be having different acceleration. So the summation of forces simply cannot be mass times acceleration of any point. It just has to be a given point, and that given point turns out to be the center of mass. So that is a tiny change that is there with forces. Now there is an additional equation. So this is the linear momentum balance equation. Okay. Now there is an additional equation, angular momentum balance, and there summation of all the moments due to all the forces. So all I'm doing is Ri cross A phi. Okay. But this time Ri is being measured with respect to some point O. Okay. And that is going to be that I matrix that we talked about, again calculated with respect to O. Okay. Times the angular acceleration. Now, what is this point O? Although dynamics of rigid body is not included in your syllabus, I'm just bringing in tiny bit of dynamics of rigid body over here. This rule, this sum of moments equal moment of inertia matrix times angular acceleration. This rule only applies to certain set of points, certain set of reference points. Okay, what are those reference points? If the point is fixed in space, the object may be moving, but if you are taking the moment with respect to a fixed point in the space, okay, or if the point itself, the O point, reference point, is the center of mass, or the O point is, not a fixed point, not center of mass, but moving with a constant velocity, or that is without any acceleration, or this one has an acceleration, but the acceleration is, it has a certain velocity and certain acceleration, but the acceleration is towards the center of mass. That means point O is such a point whose acceleration, if non-zero, is towards center of mass. Then only this relationship can be written. Otherwise, there is an issue with non-inertial reference frame and so on. Okay, so let's not go into there. Now you see that what matters for the right hand side, which is the response. This is the input, the right hand side is the response. Now, how is the input effective? The point of application of individual forces matter. Okay, but if you take a couple, okay, because of the fact that this one is F and this one is minus F, what really matters, okay, is their plane of application and the product F times T. These are the only two quantities that matter. That means the vector that is normal to the plane of application of these two vectors, that becomes the direction of the moment, and the magnitude of the moment becomes simply this distance between the two forces, the normal distance, the minimum distance, and magnitude of one of the forces. Okay, that's what that matters. Okay, so if if there are only two forces, F1 and F2, which are where f1 is plus f and f2 is minus f. Okay, and if you substitute that expression over there, so the input to this system, the system may be represented with the moment of inertia matrix. So the input to the system becomes independent of the original forces and their original directions. Okay, and their original point of application. What matters only the direction of the moment and the magnitude of the moment. So magnitude, direction, and unit. The actual line of action, the actual point of application doesn't matter. Again, this equation itself have no place for line of action and point of application. This equation only takes care of the magnitude and the direction. Okay, and when you do this calculation, you would see whether you take O to be center of mass or a fixed point in a space or any arbitrary point which is accelerated towards the center of mass. With this couple moment, you are getting the same moment value. With this couple, you are getting the same net moment because of that. We will see that in a later class. And because of that, on a rigid body, the couple moment, for the couple moment, the actual point of application, forget about actual point of application, even the actual line of action doesn't matter.
So, sir, can we say that the first three attributes are the most necessary for the vector,
The fundamental one. The fundamental
and
one, yes.
last two are used
Last
just
two are
for situation based.
Yes, situation based. That's why you never heard of these two. The line of action. This is the first time you are hearing about that line of action and the point of application being the attributes of a vector. You have only heard about direction and magnitude and unit, of course, right? Because those are the fundamental ones. Those have to be there. Okay. Achha. Last thing that I want to discuss today. Okay, so the last thing that I want to discuss today is the class timing. So, are you fine with this timing for Wednesday from 7 to 9? Are you fine with that?
Sir, if daytime will be, then that will be beneficial because of this time we have our tuition.
No. 7 to 9, this timing that we just use, is it okay or it's not?
Not, sir.
Okay,
Not
what
for
time would
me.
be? Huh? Sorry?
Not for me. Not for me, sir.
Not for you. Okay. So what time would be good? I'll tell you why I want to have. See, the problem is on Mondays and Wednesday, I have an early morning class, 10 o'clock. Okay. And if by chance I'll have to visit university, okay, which I have been from January to March. So I can do that after the early morning class. Okay, but once I'm at the university, it would be really difficult for me to conduct an online class because I don't have the setup to conduct an online class there. I don't have my graphic tablet there. I don't have the web, sorry, not webcam, the microphone, etc. So I have a computer with none of those facilities. So from the university, no, let me finish. Let me finish. So the thing is, I won't be able to conduct an online class from the university. So maybe when I come back to my house, okay, so on Mondays and Wednesdays, okay, either Monday or Wednesday, I want to have a 2-hour class from 7 to 9. Okay, the other class
so
we can
instead of Wednesday and Thursday 1 hour each, we'll have one continuous class of 2 hours.
Sorry, I can get you.
Sir, in our routine, sir, there is a 1 hour class on Wednesday and there's a 1 hour class on Thursday. So, are you saying that instead of those 1 hour 2 classes, we'll just have one class of 2 hours continuous?
Yes. First of all, I want to take a couple of 2-hour classes, and this is my plan. It is rather easy for me to have the 2-hour morning class in the weekend. So maybe Saturday from 10 to 12 I can have a class, okay, and then on Wednesday from 7 p.m. to 9 p.m. Okay, and if you are not okay with Wednesday, we can also try having the class on Monday. Does this sound? Does any of this sound okay to you?
Yes, sir. Wednesday time is fine for most of us, sir.
Wednesday time is
Wednesday time is fine.
It's
Can
fine
the
for most
Saturday
of us.
class be changed?
Saturday class is an issue.
Yes, sir.
Yeah,
Slightly.
can it be shifted to some other week, evening in the weekday? Then it will be beneficial.
Actually, I wanted to have at least one morning class. Anyways, so maybe we can do Mondays and Wednesday in the evening, 7 to 9.
Yes, sir. No issue.
Yes, sir. Yes, sir.
Yes, sir.
Okay.
That's
Yes, sir.
fine.
That is fine for most of us, I think.
Okay. What about you? You said Wednesday would be a problem.
Ishad, I think sir is talking to you.
Okay, maybe we can think of that in the next class. So let's try Monday 7 p.m. next week.
Okay, sir.
Okay. Okay, so see you on Monday.
Thank you, sir.
Thank you, sir.
Thank you, sir.